Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video, I will implement the famous ResNet architecture from scratch with PyTorch, and I will do it on Cypher10 dataset. Now, Cypher10 is a dataset, image dataset of size 32 by 32 by 3 channels, and hence I have to tweak the ResNet slightly because original ResNet mostly was built on ImageNet dataset, which was 224 by 224 in sizes. And so for the Cypher10, the specific ResNet architecture that I will implement will be ResNet 56. Let's jump in. So here I'm looking at the original paper of ResNet that came in December 2015, and the graph that you see here, that kind of denotes the main problem of a deep learning network before ResNet. That is, when the network becomes deeper, this gives a higher training error and as well as a higher test error. So the fundamental problem is that theoretically, when I bring in more and more layers, that should improve the accuracy of the model. But actually, in practice, when for a much deeper network, our error rate actually increased, and that's the problem that ResNet solves. So the most crucial part of the ResNet is this thing called the skip connection, or the residual connection here, that you can see that here the mapping is to be to this function fx plus x, and this output here is connected with an variable x that is coming from two layers behind this step. And that's very much the most fundamental key points in ResNet. So here the network can learn more complex features, but it also going to have these skip connection, that is the identity mapping from what is previously computed or previously learned. So the network can kind of choose what it wants to have in its learning journey. Basically, it can remember what is learned before. That is, this x that was learned before, that is being added here at this layer, skipping to connection. So more in layman terms, that the key point here is the network can learn new things, but it's at least never going to forget what it learned before. So in theory, it should never become worse as we increase the depth of the network. And this same paper gives this very famous diagram of ResNet for various layers, that is 18, 34, 50, 101, 152 layers. And let's talk about ResNet 50 layer a little bit. The architecture of ResNet 50 has 4 stages. This is one stage, next stage, second stage, third and fourth. And the network can take the input image having a height and width as multiple of 32 and 3 as channel. For the sake of explanation, we will consider the input size here to be 224 by 224 into 3, because most of the ResNet model were tested on ImageNet dataset with this size of 224 by 224 by 3. And you can note that every ResNet architecture performs the initial convolution and max pooling using 7 by 7 and 3 by 3 kernel size respectively. Afterwards, stage 1 of the network starts, and it has 3 residual blocks containing 3 layers each. So in the first stage, I will have this block occurring 3 times. That is, I will have 9 convolution here in this block. Then in the next block, I will have these repeated 4 times. That means I will have 4 into 3, that is 12 convolutions. Now let's quickly see why does ResNet works at all. I have 2 neural network, A and B. The A does not have any residual layer, so here the input X is passed through these neural network to give my activation A1 here. And then in B, that's a deeper neural network, and here I have a residual layer with 2 layers, extra layers, and a skip connection. So my input X is passed to A1, and the activation A1 is passed through these residual blocks to give my final activation A3. And now let's see the value of A3 for this B neural network. So first assume there is no skip connection. In that case, A3 would be just this function, ReLU of W2A2 plus B2, where W2 is my weight, B2 is my bias, at the layer L2, and A2 is the output from layer L1. But with skip connection, this term A1 need to be considered for calculating the value of A3, because skip connection means this A1 is getting added through skipping this layer to my A3. So then the equation becomes this, that is A3 equal to ReLU, then W2.A2 plus B2, which is the same as we had previously. To that, I also have to add A1. And now the important part, that if we use L2 regularization or the weight decay algorithm here, that means, that is by the definition of weight decay algorithm, that it will force W2 and B2 to become close to zero. That's how the weight decay with L2 regularization works. So in the worst case, these two terms, W2 and B2, both become zero, and then A3 just becomes ReLU of A1. And because ReLU will output 0 for negative and A1 for positive, and we know this A1 is actually the previous activation coming from the previous layer. So that means A1 is positive, which means A3 equal to A1. This means that identity function is easy for residual blocks to learn, because this is an identity function, that is the output of this function is the argument of this function itself. ReLU A1 is equal to A1. That is just the pure definition of identity function. So by addition of these residual block, model complexity was not increased, as this is only copying the previous activation to the next layer. But it may turn out that these additional layers learn something useful. In that case, network performance will improve. Hence, the key point is that adding the residual block or the skip connection does not hurt the network performance, but in fact increases the possibility or the chances that new layers will learn something useful by remembering things from the previous layer, that is from A1. Now quickly see some of the basic concepts of the residual ResNet architecture altogether. So one is basic block versus bottleneck block. So in this picture on the left, I have a basic ResNet block. This is composed of two layers of 3x3 convolution, batch norm, and ReLU. In this picture, the line here represents the residual operation, and on the right I have a bottleneck block. It has the skip connection skipping three layers in between. So to increase the network depth while keeping the parameter sizes as low as possible, the authors defined this bottleneck block. Here for each residual function f, 3 layers are stacked one over the other. The 3 layers are 1 by 1, then 3 by 3, and another 1 by 1 again, where these 1 by 1 layers are responsible for reducing and then increasing the dimension, leaving the 3 by 3 layers a bottleneck with smaller input and output dimension. That's why it's called a bottleneck. The next concept is on identity block versus convolutional block. So in this picture above, it represents all these lines, that is the solid black lines representing the skip connection. They represent identity block, and this dotted line that represent conv block. So in the identity block, the first one, that is has no convolution layer at shortcut. In this case, input has the same dimension as output. In the identity block, the input of the block is added to the last one right before the final activation function. The connection from the input to the add operation is called a skip connection, or sometimes it's also called a shortcut. And now the conv block, that is with the dotted line, here the difference is that this time the skip connection passes through an independent convolution layer before being added to the output of the third convolution layer. This layer has a kernel of 1 by 1 and uses strides of 2, which has the effect of changing the dimension of its input. So the convolution block is used whenever you need to change the dimension in order for the output and input dimensions to match. That being said, how do you change the dimension of a certain volume using convolutions? Well, you change the dimension with stride. And now just a quick sanity checking of these calculation of this output size. So we will just see how a single convolution changes the input size from 224 by 224 to 112 by 112, and then you can actually apply the same calculation for calculating the output shape for the other layers as well. So here in the first conv1, I have the input from ImageNet dataset, which is the size is 224 by 224. It is actually mentioned in various parts of this original paper as well. Now let's quickly calculate, apply this formula to calculate the output size. I have 224, and looking at the output size here, that is 112, 112. I can infer, you have to actually infer the padding. There was a 0 padding added 3 times on each dimension, and that's why you are getting this calculation here. That is 224 plus 2p, that is 2 into 3 here, and the kernel size was 7. As we saw that 7 by 7 is kernel size, stride of 2, and so you apply kernel size of 7 divide by stride of 2 and plus 1, and that gives you 112. And that's how you get these calculation here. That is 224 becomes 112, and then in the next conv again this will become 56 by 56, because again similar calculation will be applied with a stride of 2. And another important point to note from these architecture is these numbers here. That is how 64 is becoming 256. So if you look at the input channels of each of these stage, you can see this pattern. For the second stage, that is the second ResNet block, the input channel is 128, that becomes 512 at the end. Similarly, for the third one, 256 becoming 1024 and 512 becoming 2048, and this pattern is applicable here as well, and for the 152 layer as well. So what we are seeing is that it's always going to be 4 times the input channel at the end of that particular ResNet block, and this particular feature will be needed when I start implementing the architecture from scratch. That is that will determine how my padding calculation will need to be, because this difference is also going to be my padding to add, because to match the dimension between 2 layers I need to increase the padding by the same number of differences. We will see this in a second when we get into the code of the architecture. So to summarize the entire architecture and the motivation of ResNet is that without the skip connection methodology of ResNet, in a deep neural network we face something called vanishing gradients and the curse of dimensionality. What it means is that if we keep increasing the number of layers, we will see the accuracy will saturate at one point and eventually degrade. And this is called the degradation problem in a very deep neural network. So under this problem, we know that shallower networks perform better than the deeper counterparts. And here comes ResNet to solve this problem. So under ResNet, we ask the fundamental question that why not skip these extra layers and at least match the accuracy of the shallow subnetworks. But how do you skip layers? You can skip layers by training fewer layers using the skip connection or residual connection. This is what you see in this image here. And if you look closely, as we saw earlier, that we can directly learn an identity function relying on skip connections only. And this is the exact reason why skip connections are also called identity shortcut connections too. And now, before the actual coding to implement the architecture, let's go through what the paper talks about implementing ResNet on Cypher 10, because I am going to follow exactly this architecture, because the overall this ResNet paper was implemented keeping the focus on ImageNet dataset, which is a 224 by 224 dataset. But for Cypher, for implementing ResNet on Cypher 10, we have to make slight changes, and the paper actually talks about quite a bit of things about implementing the same architecture on Cypher 10. So I'm going to follow exactly these architecture for Cypher 10. So let's see. So in this section, 4.2 section of the original paper, that's what I'm looking at. And here they talk about the network. We conducted more studies on Cypher 10 dataset, which consists of 50K training images and 10K test images in 10 classes. The network inputs are 32 by 32 images. That means these Cypher 10 is 32 by 32. With the per pixel mean subtracted, the first layer is 3 by 3 convolutions. Then we use a stack of 6n layers with 3 by 3 convolutions on the feature maps of size 32, 16, and 8 respectively, with 2n layers for each feature map size. The number of filters are 16, 32, 64. The subsampling is performed by convolutions with a stride of 2. The network ends with a global average pooling of 10-way fully connected layer and softmax. There are 6n plus 2 stacked weighted layers, and then they give the following table summarizes architecture. So for 32 by 32, I have 1 plus 2n. 16 by 16 map size, I have 2n layers, and another 2n for 8 by 8. When shortcut connections are used, they are connected to the pairs of 3 by 3 layers. On these dataset, we use identity shortcuts in all cases. Okay, this is very important. Let's just 1 second. This part, because my architecture will implement this. On this dataset, we use identity shortcuts in all cases. That is option A. And so our residual models have exactly the same depth, width, and number of parameters as plane counterparts. We will come to this point. What exactly is option A that they're talking about? This is given somewhere else in the paper. But let's see some other important things. We compare n equal to 3, 5, 7, 9 leading to 20, 32, 44, and 56 layer network. So I'm going to use for this implementation these 9. That means the total number, the 56 number is coming. If you multiply, you have to take 6n plus 2. There are totally 6n plus 2 stacked weighted layers. So if you multiply 9 into 6 plus 2, that gives me 56. And that's how I'm going to implement ResNet 56 on my Cypher 10. So about these option A, that is for doing the identity shortcuts in ResNets. Let's go where they talk about that in detail. Yeah, here. So first look at these dotted line. They represent the identity mapping. So the identity shortcuts can be directly used when the input and outputs are of the same dimensions. That is all these solid lines. But when they are not of the same dimension, that is in this dotted line, look at this. From 64, I'm increasing to 128. Similarly, here for this dotted line, from 128 to 256. So there is a size mismatch here. So, and here, the way to tackle these size mismatches are very well explained here in this part of the paper. That is, when the dimension increase, dotted line shortcuts in figure 3, we consider two options. Option A is the shortcut still performs identity mapping with extra 0 entries padded for increasing dimensions. This option introduces no extra parameter. And option B is the projection shortcut in equation 2 is used to match dimension done by one convolutions. For both options, when the shortcuts go across feature maps of two sizes, they are performed with a stride of 2. All right, so these are the two options we have to tackle the situation, that is to tackle this mismatching of sizes. And so the option A is just zero padding. Option B is done with one convolutions. And for cipher 10, they clearly say that we have to use option A, that is doing a zero padding to the input tensor. And that's what I'm going to do in my code as well. And here I am in my VS Code. Initially all the regular imports from Torch and Torch Visions, and then I'm checking my GPU while running in Colab. And from here starts the main crux of the story, that is implementation of ResNet with PyTorch. I'll be having 3 class: lambda layer, basic conf block, and also ResNet. And most of my 99% of my work will be done between these two classes, that is ResNet and basic conf block. The lambda layer class, it is just a very simple interface to implement a lambda function later within my basic conf block. And all it is doing is it is returning my input x with a self.lambd. That's how I'm naming it. So we'll see this usage of these in a second. So now come to basic conf block. Now this class, what they are basically doing is they will implement two things. I put that in my comment here, that will implement the regular basic conf block plus the shortcut block that does the dimension matching job. That is what we discussed a while back, that is option A or option B, when the input dimension and the output dimension does not match between two layers. So this basic conf block will just implement those two job here. And so otherwise the basic conf block takes an input within channels, applies some blocks of convolution layers to reduce it to out channels and sum it up to the original input. If their sizes mismatch, then input goes into an identity mapping function, which will be done here, the shortcut block. Okay, now on the basic block, the first thing is I have to do the basic convolution work. And this convolution involves a conf 2D layer, a batch norm 2D, a ReLU, then another conf 2D, another batch norm 2D. Now I'm including all these different layers inside nn.sequential and then an OrderedDict. So let's see why I'm using an OrderedDict here. And before OrderedDict, just quickly note that in my convolution I'm using kernel size of 3. Stride is coming from my argument, and padding is 1. And this kernel size is exactly following the architecture as given in the paper. And also another point, that I have one conf 2D and one batch norm 2D and then a ReLU. But then for the next conf 2D I have batch norm after that, but there is no ReLU after this. All right. And now why I'm using OrderedDict here. First, OrderedDict is a dictionary subclass that remembers the order that keys were first inserted. The only difference between dict and OrderedDict is that OrderedDict preserves the order in which keys are inserted. A regular dict doesn't track the insertion order, and inserting it gives the values in an arbitrary order. By contrast, the order the items are inserted is remembered in the OrderedDict subclass. Now nn.sequential, that is this function here, takes as argument the layers separated as sequence of arguments or as an OrderedDict. Here I am assigning a name here, that is my whole all these operations, that is 2 convolution, 2 batch norm and 1 ReLU. These operations are being named as features. and hence it's better to pass an instance of OrderedDict to manage these operations. And also self.features can act as a module dictionary container with the use of OrderedDict. Self.features, in this case, our neural network equals nn.sequential with an OrderedDict of various layers as an argument. And now the most important part, and little tricky, this one, that is my shortcut layer. Now, the main point to remember that we use identity shortcuts when input and output channel dimensions are the same, but otherwise when input and output spatial dimension don't match, we have two options. Exactly what was given in the paper, that is, the two option is option A, use identity shortcuts with zero padding to increase channel dimension, and option B is to use one by one convolution to increase channel dimension. It is also called a projection layer or projection shortcut. Let's just quickly look at the paper again, because this was clearly mentioned in the paper. So again, I'm looking at 4.2 section where they're implementing Cypher 10, implementing ResNet on Cypher 10. So it's clearly written, when shortcut connections are used, they are connected to the pairs of 3 by 3 layers. On these dataset, we use identity shortcuts in all cases, that is option A. So our residual models have exactly the same depth, width, and number of parameters as a plane counterparts. All right, so that's what I'm doing here. And also note that before applying the shortcut, I also have to check these conditions, that is stride is not equal to 1 or in channels not equal to out channels. Obviously, this is obvious because that's why I am doing the shortcut here, that is to match my in channels and out channels with the use of either padding, zero padding under option A, or using a conv under option B. So under option A, I have to do two transformation to the input x variable. That is, I have to implement a stride equal to 2 and also implement the padding and get the proper padding number. So let's go through these through the single line of code one by one. It is just this single line, but it has got some tricks included it. So first, this f.pad, that is functional.pad, PyTorch's nn.functional.pad takes the first argument is the input, which in this case is x. But let's see how I'm changing this x with the slice notation here. This slice notation, that is colon 2 and the colon 2 actually is doing the job of implementing stride equal to 2. Now let's see how. So let's say I have a variable something like this, x equal to a b c d e f g h and so, and if I do x, then colon 2, that will actually output these one, a c e g. You can see that every second element is omitted in here. That's because the slice notation works like this, that is, the first colon actually represent my starting position, second colon represent my stop position, and the third one represent my step, that is how many step I should omit. And here this double slice actually means, it reads like this, that is default start index, default stop index, and step size is 2. Now default start and stop is the first position and the last position by default, and now by mentioning step size equal to 2, I am omitting each of the second element. I am omitting b, then I am omitting d, each second element. So effectively it's the same as stride, that is I am stepping over one step by jumping over one step. That's what stride equal to 2 will do. Now coming back to my code, so that's what this is doing. And remember, x here is a 4-dimensional tensor. It has In PyTorch, the first dimension is the number of samples in a batch, then number of channels, then height and width. So it's a 4-dimensional tensor, and I'm applying these double colon notation to my height and width dimension. That means it will jump over 1 pixel in here. So that was my transformed input, and now coming to my the second part of this f.pad. Here I am actually mentioning how I want to apply the padding, and here there's one thing to remember. You can actually go through the f.pad documentation to understand it very well. So how this will work is that let's first come back here. So the padding lengths are specified in reverse order of the dimensions, where every dimension has 2 values, one for the padding at the beginning and one for the padding at the end. Now we know that in PyTorch the dimensions are mentioned as batch size, channel, height, width. But for mentioning the padding, I have to reverse it. That is, width will come first, then will come height dimension, then channel, last will come the batch size. So I'm just mentioning it here in a little bit more detail. So for an image with dimension channels, height, width, the padding is given as width beginning, width end, height beginning, height end, channel beginning, channel end, which can be reworded to left, right, top, bottom. That means following that kind of notation, that is reverse order of dimension, what here it means is 0 0 here means width beginning, width end, both are padded as 0 0. Then I have height beginning, height end, again 0 0. Then I'm actually adding my pad to add. This will be some numbers, not 0. And what this represent? These represent my channel beginning and channel end. And again the last one, these 0 0 represent batch length beginning and batch length end. Now look that note that I'm including 0. I'm giving 0 to all the padding, that is to width, height, and my batch length. All I'm giving 0. Only thing where I'm actually giving some numbers to the pad is my channel dimension, and that's the purpose of my shortcut layer, that I am increasing my channel in the shortcut layer. Now this pad to add, this number will be my out channels divided by 4. And this double forward slash just means that I will need to have an integer after the division. I cannot accept a float here. I need to have an integer, and that's why I'm using the double slash. So this pad to add is out channels by 4. Let's see why that is. So I'm coming back to the original paper here, as we discussed it already, that if we look at this architecture table here, these input number 64 is becoming 256 in the first conf block. That is, the 64 is multiplied by 4 to give me 256. For the second ResNet block as well, 128 becomes 512 channel. That is again 128 multiplied by 4 gives me 512. Then the third conf layer as well, 256 multiplied by 4 gives me 1024, which is the number of channels at the last layer of this third conf block. So what it does is that the multiplier is always going to be 4 times the input channels at the end of that particular ResNet block. And that's exactly the reason I am getting the same number as my pad to add. That is, out channels divided by 4 is the number of padding numbers that I need to add to my channel to adjust for the mismatch. And that's the reason I'm doing this line here. All right, so I think this is now pretty clear. We just explained every part of this code here. And now the option B is rather simple, that Here I for adjusting for the mismatch of dimension, I only do a conf 2D with my in channels and 2 multiplied by out channels. Kernel size remains 1 by 1 because here to make up for the mismatches of size, I have to do a 1 by 1 size kernel, and then I'm also doing a batch normalization. That's pretty much option B. But remember, for Cypher 10, as per the requirement of the paper, we will not be using option B. Rather, we will be using option A. So that was my shortcut layer. So features and shortcut both are done. So in this basic conv block class, I'm only left with the forward function, which is super simple. Because here under the forward function, I just have output. The first output will be from the self.features, which will do all these standard convolution operations, and to that I just have to add my shortcut layer output. And remember, this is the crux of the whole ResNet, that I am adding my previous layer's output to my current layer, and that's why this plus equal to sign is here. That's the only difference from a normal convolution layers forward function with the ResNet's forward function, that here I am adding the output from the previous ones. So here I'm just accumulating this value of the result of the features, and then I'm adding self.shortcuts. That is, I have to add the result of self.shortcut as well. Finally, a ReLU layer, and then that's my output from the entire class. All right, so tricky part is over, and now this ResNet class is comparatively much easier. But before going into this, just understand one thing, that in ResNet, each block consists of many convolutional layers, and hence in this class there will be a method build layer here, which will generate many individual convolution layers, and then within these blocks I will just stack those individual layers. That's pretty much this class will do, that it will repeat the layers and then stack the layers to each ResNet block. Now see what I'm doing here to implement that. So first, within my init constructor here, and this class takes a block type and num blocks, only these two arguments, and block type would be my this previous block, previous ResNet block that I have written earlier, that is basic conv block, this class. That will be my block type here, and number of blocks, this will be an array of numbers, and so here in number of blocks I will be specifying how many layers in each block I want. So in this case, for Cypher 10, I'm implementing ResNet 56. That means I need to provide it number of blocks like this, 999. So each block will have 9 layers, and so that's number of blocks list. So let's come back to here. So first, see this build layer function, because this is the function with which I will be building this individual 3 blocks. So build layer will just take block type, out channel, number of blocks, and starting stride. Now about the starting stride, let's go back to the paper for understanding the starting stride. So this is what they say, that just read this one here, this line: for both options, that is option A and option B, which we discussed earlier, when the shortcuts go across feature maps of 2 sizes, they are performed with a stride of 2. This is because here in ResNet, reduction between layers is achieved by an increase on the stride from 1 to 2 at the first convolution layer of each block, instead of by a pooling operation. And so if I go to these image again, so here when the dimension changes between 2 layers at the junction, when the dimension mismatches happen, the reduction is performed with a stride of 2, and that's at the first layer, the first convolution of each block. And that's why I am in my build layer function using a separate argument starting stride, because this is what needs to be mentioned. So yeah, so that's about starting stride, and then I'm just creating a list of strides. That is stride list for current block. That will be just an array of strides, which the starting stride will be obviously this one, and the rest will be all the rest of the strides. So for example, let's I just want to show it here. So I actually printed this statement here. I have commented out loud. So if I print this statement, it will be something like this. So my list of strides for my number of blocks will be something like this. So I have 999. That means each block will have 9 convolutions, and so I need 9 strides. And the starting stride I'll be mentioning, and the rest of the strides all be will 1. And that's exactly this line is doing here. Starting stride plus 1 in square bracket, and the number of blocks minus 1, and that will give me my strides. And then my build layer function can actually run a loop to create all the individual layers with this loop here. So first I'm just declaring a list variable layers, because that's where I will be appending all the individual layers, convolution layers that I will be creating. And then in this loop I am just looping through it, that is looping through the strides for current block, and then to my layers appending these convolutional block. So block type again coming from argument, and self.inChannel, self.out, and then out channels coming from out channels coming from the argument, and stride also is part of the stride list. And then after each layer, then I will be changing the in channels to be like this. Self.inChannels now equal to will be out channels. And finally, from these build layer function, I am returning all these stack of layers. That is, build layer will build 9 convolution layers, and that will be returned from this final line, returning line. So this build layer, this build layer structure is used in many implementation of ResNet by many famous repository in GitHub. Some people name it as make layer, but the overall configuration and overall structure remains the same. That is, this function just creates 9 layers given input channel, output channel, block type, and starting stride. And then now that my build layer is done, I can have 3 separate blocks, because each of this block will have these 9 layers, and that will be built with this function. So that's exactly what I'm doing here. Self.block1 self.build layer, then block type again coming from the argument, which will be my ResNet, basic ResNet block that I have wrote earlier, and then passing the out channels, number of blocks, starting stride. And note that how I'm changing the out channels here to be so this entire architecture here is I'm implementing it on Cypher 10. So this is ResNet 56, and accordingly I have kept the out channels to be consistent. And all right, number of blocks will just be 0, 1, 2, and they all of these 0, 1, 2 will be 9 in this case. That's I will be deciding here. That is, num blocks will be a list of 9, 9, 9. And all right, so after these 3 blocks, I will be adding another average pool layer, and which will be nn.adaptive average pool layer, and lastly linear layer, because finally I need to output 10 different classes, and that's why to my linear layer the second argument is 10. All right, now I think I'm ready to go to the forward function, and forward function is nothing. It just invoking each of these blocks and average pooling and linear, all of them one by one. So first one, we can just check. We can just follow these sequences here to do my forward function. So Yeah, first one is ReLU, then block 1, block 2, block 3, and obviously we all know forward function, the output of one layer goes to the input for the next layer, and that's exactly what is happening. Output from the first line is going to the input of the second line, then again output from the second line going to input of the third line, and so on. And finally my linear layer output is my final output from the forward function and also from this class. And with that, my architecture is pretty much built. Now I just need to invoke this architecture on Cypher 10 and do the training. So in the next cell, I am just creating this ResNet 56 method, and it's just a single line. That block type will be my original basic conv block class. Number of blocks, as we discussed many times, it will be 999 as a list, because each of these 9 will create 9 convolutions, and then that will be added to one single block. The next 9 again will create 9 convolution, which will be added to the second block, and the third 9 will be added to the third block. And then in the next line, just I'm invoking this function model equal to ResNet 56. And first I just want to create a summary to check how it is performing. Yeah, so device is obviously, it's a very common code to use my GPU if that is available. So model.summary outputs this output here that we see here. And remember, in the model.summary I passed only these numbers as tuple, that is 3 and 32 height and 32 width. So this is my model.summary. Actually this is not showing in a very pretty format, so I can just open in a text editor, and here you can see that is the first one will start at this -1 is this one is to be inferred, and it's actually representing the number of samples in a batch. Otherwise 16 channels, 32, and then it goes on up to here, then it becomes 32 channels, 16 by 16 height and width, and finally from here it's 64 channels and 8 by 8 height and width. And remember, because the height and width is changing from 32 then to 16 and then to 8, because the starting stride at this juncture, that is when it was changing from 32 to 16, as the starting stride here was 2. Again the starting stride here was 2, and that's actually reduced the height and width by half. And yeah, so that's my model.summary. Now I have to train it. Okay, before training I have to load my Cypher 10 dataset. This is all very boilerplate standard code. So I have a simple function, data loader Cypher. It is just making use of torchvision datasets.cypher Cypher module that will bring your dataset to the drive. So you can either download the data to your local drive in Google Colab or whatever you want. And then I'm splitting this dataset with the random split to from the trained dataset itself. I want to have a validation part. So from the entire 50,000, I am splitting 45,000 for training and 5,000 for validation, keeping the batch size at 32, and ultimately using the data loader function, the widely used data loader function of PyTorch, to fetch my data loaders from the original train dataset, validation dataset, and test dataset. And finally, from this function, I'm just returning the 3 loader, that is train, validation, and test. And here, just to check that this is working, I just ran this, invoked this function, data loader Cypher, and it clearly said training set is 45,000 images, validation 5,000, test set is 10,000 images. And now I am fully ready for the actual training. Before that, because it's a multi-class classification problem, obviously I have to use the criterion as cross entropy loss, and for the optimizer I'm using Adam. Learning rate, I'm keeping it at 0.01. Obviously better to keep even smaller, like 0.001, but here I just want to finish the run the training properly faster to see that it's working, and I'm getting kind of a good reasonable result. All right, now my train model, this is the training model function, and obviously this function is built following just the regular configuration, nothing too complex here. That is, initially I'm defining epochs, train sample number 45,000, obviously that you already saw, and I'm defining two arrays, a list of arrays to hold on to my cost, which is my train cost and validation cost. Now in the training phase, I'm just running two loops. Again, this function is following the standard way of doing a PyTorch training that you will see in many projects across GitHub, Kaggle, or anywhere in online blogs, etc. So I'm running two loops. The outer loop is going over each epoch, and the inner loop is going over each batch from my train loader. And if you look at the inner loop, when I'm looping through the train loader, it will give me inputs and labels, and I'm transferring them to the same device, which is kind of standard. Then for every mini batch during the training phase, we typically want to explicitly set the gradients to 0 before starting to do backpropagation, and that's what I'm doing here, optimizer.0grad. Then the next line, I'm starting the forward pass, which will in this phase, first I have to get the prediction, which is my model, which is already trained, and then to this model I'm passing these inputs, and then I'll get the loss function by invoking my criterion. To the criterion I'm passing the predicted, that is a prediction, this variable, and labels, that is a prediction value and the ground truth values. Now from these, on this loss, I will do the backpropagation, and also after doing the backpropagation, then the next standard line to update the weights with a step method. And now that backward backpropagation and has been applied and weights have been updated, I can get the actual prediction by using torch.max values. That is what I'm doing here. That is torch.max. To this I'm passing prediction.data and across a dimension of 1, which will give the maximum along the rows by using the dimension equal to 1. And after getting the predicted outputs, I can have my the accuracy calculation. So that's what I'm doing in this line. Update the running corrects. The correct train will just be where the predicted outputs equal to labels that I am converting to float, sum, and item. Again, very standard code here. And finally, I'm computing the batch loss. Remember, till now, this loss is an average loss for this batch. I have to kind of unaverage it. And to do that, I have to multiply each average loss, that is average batch loss, with the batch length. And the batch length is input.size 0. Again, this is super standard. You will see this in many code implementation in with PyTorch deep learning training. So this line is doing just that, on averaging the batch loss, and this will be my train running loss. And I'm using loss.data.item because just this loss doesn't have a float value; it has gradients included within it. So with the invocation of this item method, I'm getting the actual float value of the loss. And to that, I'm multiplying the batch size, which is inputs.shape, and take the 0th element. So this is where my batch is done. And now when similarly all my batches are done, then I'm ready to calculate my entire epoch loss, epoch accuracy, things like this. So after this inner loop is done, outside of this loop, I will be doing my train epoch loss calculation. That is just train running loss divided by train sample number, which is 45,000. And train cost.append. So yeah, so now that my training this epoch loss is calculated, I just need to keep a record of this to keep a historic track of this epoch loss, how they are improving throughout across the epochs. So I'm appending these epoch logs to this list so that later I can see all the epoch lost and I can do a nice plotting of them. Yeah, and the train accuracy is as well correct train divided by the total number of samples in the training dataset, which will be 45,000. And then all these calculation, the training is done on the training dataset, and exactly the same similar calculation I'm doing for my validation dataset as well. So only thing is here there is no epoch and no batching, because this is validation dataset. So again, the same steps. I'm just looping over the val loader, which will have the 5,000 number of samples, and then I'm calculating the prediction, that is a forward pass, compute loss, compute the actual predicted values of the outputs, or that is the labels, by using torch.max, and then calculating the correct value where predicted is equal to the ground truth, and finally calculating the validation running loss exactly in the similar way like the training dataset. And finally, out of this loop, I'm calculating the entire each epoch's validation loss, each epoch validation accuracy. And this is just some printing statement that to see my training. Moving on. And finally, I'm just saving this model with the state dict, because I need to fetch this model again while testing it on my test dataset. So yeah, so this line will just save the model, and finally from the training function I'm returning train cost and validation cost, which will have the whole list of epoch losses. And so here in the next line, I was actually invoking this train model function, and you can see that I ran only for 15 epochs, and that kind of gave me later we will see what kind of test loss we got for this. So 15 is a very low number. You should run at least for 50, 70 or 100 even. And all right, so that was my training. And then before testing the dataset, before testing the model, I also have to load my model after the training. So in this cell, that's what I'm doing, that model.load state dict method that will load my previously saved model. And yeah, and then test the train model on test dataset. And this is the final part of this journey. So test sample numbers, you earlier saw that it was 10,000. I'm just defining a variable for it. And again, this code is exactly the same what we saw inside my train function for both training dataset and validation dataset, except that here there is no epoch, there is no batch calculation, because it's just a I'm using the trained model on my test dataset to get the actual prediction, the actual accuracy. So I'm just looping over single loop, and I'm doing torch.nograd because I do not need to calculate the gradients here, because I'm not training the dataset here. I'm already using the pre-trained model. That's why I'm using this context manager kind of thing, torch.nograd, by switching off the gradient. And a single loop here that I'm looping over the test loader. And again, calculating the prediction, calculating predicted class with torch.max, calculating my accuracy, that is a actual correct prediction where the predicted class equal to labels. And finally calculating test accuracy, and printing my text accuracy gave me 0.8344. Not too bad, because I used only 15 epochs, and also I used a relatively high learning rate of 0.01. So now if you do some more hyperparameter optimization here, or even run the exact same project with higher number of epochs like 70, 80, you will obviously get much better result, much better test accuracy. But anyway, this is how my entire ResNet 56 was implemented from scratch with PyTorch. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and Tensorflow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.